Let's record this session for posterity. Make sure we have there. Many people think it's going to be soup is the answer to how many people will show up in person. I could take the mask off then. I didn't need to come to this. I could do this in the comfort of my own office otherwise. But so anyway, we can end the poll. We'll see. I'll just keep doing it. Hope everybody's having a good Friday. Take a look outside. We got a little snow coming down. The campus looks really nice when it's covered in snow, in my opinion. All right, so let's see here. We will do our share application screen, and we'll go to that great cascading little thing. Whee! Okay. So sometimes what I like to do is to put when I have this and I'm all by myself, so that because I don't have dual monitors here, is to log in with my computer, and so I can maybe see the other screen here. But is the computer going to turn on? All right. While I'm waiting for that to happen here. So we have our review session for exam 1 in dynamics. Exciting. The topics that we're going to cover today, or the topics that will be on the exam, I should say, are the fundamental kinematic relationships, projectile motion, which is a constant acceleration kinematics, relative motion, constrained dependent motion, aka pulley problems, rectangular coordinates, coordinate transformation, path coordinates, and polar coordinates. It's always a good idea when you're approaching an exam to make like a list like that of your own. Try to figure out your strengths and weaknesses, where you need to put more effort. So those are the kinds of problems that we can cover, and we have a bunch of problems in the practice problems to go through. Now, excuse me as I sputter and stammer, because I'm trying to multitask here and log on so I can see any chats that might come up using my other computer here. Collaborate. I think I have to do it as a guest here because I don't think my account lets me log in twice. So I'll copy my guest link and come in as, boom. Make sure I'm muted. And we're almost there. Okay. So now I'm able to, although I won't be able to hear the ding. That's unfortunate. I don't think there's a way around that, but I'll try to look over there at the chats every now and then. Try to see, but I won't have the ding response because I have to mute it. Otherwise, I won't be able. Everybody can hear me, right? Let's see. Let's test this out. Can you hear me? Yes. Okay, good, good. I just want to double check. All right. So I take requests. We will here. First off, I'm not sure that everyone will be taking this. Not everyone here, let's say, is necessarily as their professor going to be using the equation sheet. I created this equation sheet and just figured it was just kind of better than having you make your own equation sheet. I know that a lot of people are going to be taking this remotely, so it's kind of like sort of a weird kind of thing because you're kind of like on your honor to only use the equation sheet and not. In any case, I think that this is also just a convenience. Maybe we could think of it in those terms. And I think actually I need to modify this, and actually should have done that previously right there. And let's crop this down, because only that is covered on this first exam. It used to be that we covered everything. well, not covered everything. That we used to cover a little bit of Newton's second law, and we as a faculty got together and decided, let's make the first exam only cover the particle kinematics. So here's the fundamental engineering, fundamental kinematic relationships. Here's some the special cases of using those when we have constant velocity or constant acceleration. We also have the relative motion of particles. We have the path coordinates, velocity and acceleration, and the polar coordinates, velocity and acceleration. And when you look at it like that, it makes it pretty simple, right? Pretty straightforward. Not a ton of equations. Probably the most intimidating one is probably the acceleration in polar coordinates, but we'll get by that. I have a bunch of problems. You see, let's see. Okay, so starting out right here, these are ones that I included as just sort of auxiliary or additional ones to look through to consider trying. They're projectile motion problems, and some of them this one is actually a really hard problem. Actually, this one might be as well, but I think this is a particularly difficult problem. It will not be on the exam. But I think I was putting it in here to try to give people the idea that you could take something that you think you already know how to do, a projectile motion problem, and you can just change it slightly, and it can make it into a much more difficult problem. But I think that's a little cruel. But here's like with the main ones in the packet that you should have access to. I think all the professors have given you access to this, where we have, so these are old exam problems that we used at the Coast Guard Academy where I previously taught, and I made available so that the students could, warm up, right? Help with their preparation. These are in addition to the homework problems that you've been provided, and because these were formerly exam problems, like you'll see this S16. That means in spring of 16, this was actually an exam problem that we gave. In 17, I guess I didn't give the coding here, but these, like, here's some projectile motion problems to try. Here's a fundamental engineering kinematics problem. Another fundamental kinematics, and another. This is actually combined fundamental kinematics and polar coordinates. That's a good idea to try that. Here's another one, fundamental kinematics and polar coordinates combined. And polar coordinates and constant acceleration together. Constant acceleration and path coordinates combined. This should not be in here. I keep forgetting to move that out of there. Boom. So now the numbering is not going to be correct based on the packet, I think. So we have the relative motion. That's an important thing to make sure that we're covering. So that should be like question number 10 now instead. We have relative motion and path coordinates. We have relative motion just by itself. We have constrained motion and constant acceleration. So those are the problems that we have in the packet. I also picked one last year, I think, kind of a little unwisely, and just tried it out to see if I could solve it. Just picked it out of a book and said, hey, here's another relative motion problem. And it was a pretty difficult one, like too difficult to be on an exam, but I did present it last year. So those are the problems. Does anybody have any requests? I can pick a problem, or you can pick a problem.
Hi, can you hear me?
I can hear you.
Oh, perfect. So I was looking at the exam 1 practice problems, and I was wondering if we could go over number 9.
Number nine. By the way, does anybody know what that reference is when I go number 9 like that? Anybody? I like pop culture references, so I wanted to. Well, it's actually not pop culture, really. It's a Beatles song. It's not really a song. It's actually on the White Album. They just repeat number 9 a bunch of times. But anyway, I digress. And often. Yes, we can do that. Hello. Thank you for the request. I take requests.
Hi.
I don't have any guitar with me, so I can't sing with you. Sorry.
Hello.
But I would. Okay, I also hear someone.
Yeah, that's me, Jarrell. Hello, Professor.
Hello.
Could you also do number 6?
Yes.
Okay.
We'll do number 6 next.
Okay. All right. Great.
Cool. And I will also, let's see, I'm going to take my, I'm going to cheat. I'm also going to take a little peek at my, at the solution just in case. Okay, so we have a constant acceleration and path coordinates problem. So hopefully the benefits of doing this amongst them will be as I narrate the thought process that needs to take place. Like, how do I solve this? You can barely see that car right there, right? Okay, so they tell us that there's this, a car at point A is 100 meters away from this point B, right there, along a circular track, the distance measured along the track's perimeter, and begins to accelerate from rest, right? So I guess he's going to travel in that direction. I think that's what it is. What constant speed increase is needed for the total acceleration magnitude to be 8 meters per second when they reach B? The track is 150 meters right there. So when we say the total acceleration, that should be something that jumps out at us. And maybe we want to think, well, what is the total acceleration? Well, that just means the magnitude of the acceleration. And because it's going around a curve, that ought to tell us that it's path coordinates. The problem itself did not say path coordinates, but the act that we were going around a path will tell us that. So we're going to take this, and that's going to give us that 8 meters per second squared. It's got, these are like the code words that we're looking for, that total acceleration, and we see that there's a path right there. So, in order to get this, we're going to have 2 parts. So we're going to have, this first part is going to be based on the acceleration that's taking place, right? The acceleration, like we can even think of it as being in a straight line, even though it's not a straight line, that it has 0 velocity right here, and it has to have this unknown velocity right here at this point. And that unknown velocity is going to be is going to give us that an to be equal to this. We're also going to know that it's going to travel to here, to right there. And when it does, going along that line right there, we're going to be able to fit, well, first off, we know that this distance is going to be, right? That distance is 100 meters, right? So the arc of this right in there is 100 meters. So one thing that we could use is we're going to have a velocity squared. It's going to be equal to the initial velocity plus 2 times the acceleration. It's going to be a constant acceleration. But it turns out that's going to be the tangential one. So I'll go ahead and put a T right there. And that's going to be the delta. And I'll call it S. I'll say that the delta S is 100 meters. So now I have like 2 things that I know. This is the velocity that we get to be right there, right? And this is the velocity that's going to cause this. So we actually, we have all the equations that we need. We just need to be able to like figure out how we manipulate the algebra. These are the big ideas and the concepts, and we're just picking them apart based on what we know from what we're observing of the problem. So I say, I can start replacing things that I know in here. First, it starts at rest. That helps me. And v squared is going to be equal to 2. I need to find this. I also need to have, I know what this is right here. That's 100 meters. So I could solve for this as being my v squared over 2 and 100. So what I'm going to say, and might as well square this right here, right? So I could say that v squared over 200, you know what, this is going to be v squared over 150, right? As we were told the radius of this was 150. Squared plus v squared over 150 squared is going to be equal to 64, right? So I squared both of those, so I skipped a little step right there. And what I can do right here, now I can play around with the thing and I can find out what the velocity is. Now, when you see the posted solution later, they did not approach it in the same way that I did, but I think mine's better. I think mine will be better, because I'm going to find what this velocity is going to be, and then I can just plug them back into here. I think I know who from the person's handwriting who wrote the solution to this one we'll see here. So anyway, I can take v to the fourth plus v to the fourth, and I can square 200. 200 squared is 40,000. 150 squared is 22,500. I will take my v fourth right there, and so I find the common denominator, right? Would be 22,500 plus my 40,000 divided by my 22,500 and 40,000. Did I do that right? My algebra might be like old man has to do algebra in front of young people. Pretty sad. So I think that's going to be true. I multiply them by each other. Multiply that by 64, and then I add 22,500 and 40,000. Should have been able to just do that in my head and divide it through. I get V4 is equal to 921,600, and then I can take the fourth root of that. Where'd you go? Right here. And boom. So I get 30.98, and these are meters per second. So I'm going to take that and I'm going to plug him back into here. So my AT is going to be 30.98 squared divided by 200. So square that, 200. And I get 4.800 meters per second squared, which is what we were told, yay, was the intended solution. And perplexed as you might be right now at this moment, how was I supposed to know how to do that? Well, that's what we're trying to train you to do, to take something that you haven't seen before and apply the concepts and pick your way through it. I will say this is a pretty challenging one because this is a little off the beaten track. It's not exactly, but it is sort of the thought process that you could be asked to do, like to combine ideas. Like we have that idea right here. We have this idea right here for path coordinates. We also, some of the key right here was that term right there, the total acceleration. You needed to know that's what was meant, what that means. Like, you know, interpret those words. It's challenging, I'll admit to that. Is there any questions on to this one? I'm looking down at you.
I just have a quick question.
Okay.
So, so it looks like that we solved for the tangential acceleration, but how do we know Like, how come it was we solved for tangential rather than the normal acceleration?
Because it says, it's a great question. And it does bring up a really important point. When you get towards the end of the problem, make sure you go back and see what they were asking for. What constant speed increase is the big thing that's being asked there? Does that make sense? Because
Yes.
the tangential one, okay, so another way to say this, remember that velocity is always tangent to the path, right? So, on this path right here, we have the car moving right there, there's the velocity, but that velocity is going to be equal to the speed times the tangential unit vector. So when they're asking here what constant speed increase, that's code word for the tangential acceleration, right? Does that make sense?
Yeah, sounds good. Thank you.
Okay, you're welcome. Now, if you are, by some chance, overwhelmed by this right here, have no fear. It is not, all is not lost. We're going to work together to try to incrementally get better at solving the problems. But the best way to do that is to go try some of the other problems out and just to kind of chip away at it. So here is another problem. Problem number 6, as requested. I'm making a mess of my papers here. Stick right there. Okay. All right. And I do believe that this was my problem. Maybe? Back in the day. Oh, yeah. This is mine. Okay. So we want to. So what we're given is a. Okay, this is not what we're given. This is the answer right here. That's very confusing because it's written right out there. But here we go. Pretend we don't see that at all. Right. That's the answer. The path of a particle shown in the graph is represented by these two equations, where the radius is in meters and theta is in radians and the time is in seconds. Using polar coordinates at time t equals 5 seconds, determine the velocity vector, the acceleration vector, and then sketch the velocity vector at the appropriate point. And I just want to say, this path that you see here is in fact actually plotting out those, so it isn't just some imaginary thing. Well, I guess it is sort of imaginary. Somebody's imagination was involved. So what we want to do in polar coordinates, when we see that, our brain should think, that's supposed to be a light bulb. Boop, 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 boop. What should be triggered by there is the variables of interest. And those are R, R dot, R double dot, theta, theta dot, theta double dot. So our mission, should we choose to accept it, is to try to find these in some way, shape, or form. Well, we see we have R and we have theta. So let's just go ahead and proceed through them. We say that R is equal to 1.5 plus the cosine of pi over 2t. Anytime we see this, by the way, that pi should be a hint. When we go to do cosine, make sure put calculator in radians. Because that's an easy one to mess up. So then we take it, well, what is R dot? That's nothing, right? That's going to be negative sine, right? Times the stuff that's on the inside. So it's negative pi over 2 sine pi over 2 t. We say this one is still going to be negative, but now I'm going to take the stuff on the inside again. Pi over 2 squared cosine pi over 2 time. We take theta. It was pi over 2 t squared. Theta dot is going to be just pi t, right? And then theta double dot is going to be pi. Let's put 0.5 seconds into all of these. So I purposely made them so that I could write these out. 1.5 plus the cosine of pi over 2.5. 2.207, these are going to be meters. You're going to make sure, though, as I said right here, put the calculator in radians. I don't even know if I know how to do this with this one. There's a mode. There's a mode somewhere. There you go, modes. I go to my modes, and I go radians. I think I have to click that button right there. Yeah, it tells me I'm in radians. So when I go, I should be able to do that in my head, but I'm not going to. Pi 2 divided 0.5 times, boom. So then I want to take the arc cosine, boom, and then add it to 1.5, and I get something different. Why did I get something different? That's going to be messed up. Wait a minute. How can that be wrong? It can't be wrong. I can't be wrong. Let me do it again. Pi divided by 2.5 times, all right. Inverse cosine. No, I'm supposed to take the cosine of it, dummy. Why was I taking the inverse cosine? I'm so stupid. All right, my daughter's sending me texts. Stop it. She's a character. 1.5 plus. There, I got it. Okay, I got it. Okay. I just want to double check, and I just wanted to do it live so you remember, put your calculator into radians. So I have negative pi over 2 sine of pi over 2 times 0.5, a negative 1.111 meters per second. And then a negative pi over 2 squared cosine pi over 2.5, negative 1.745 meters per second squared, pi over 2.5 squared is 0.3927 radians. But I also might want to know, I could turn these radians into degrees, because that just might be something that's interesting to me when it comes to the theta. When I see this up here, I can look over there and I can go, that as shown right there, that's this is the 22.5 degrees. Gives me a little more confidence, that's the one. Here we go, the pi times 0.5, 1.571 radians per second. And then this is just 3.142 radians per second squared. So the velocity, now we're just plugging and chugging for this one. R dot ER plus R theta dot E theta. R dot given, negative 1.111. And here we're going to take the radius, 2.207, multiply it by our 1.571. Oops. And that is going to give us our negative 1.11 ER plus 3.47 E theta meters per second. Now, personally, I think what we should have asked, find the speed. Because then you would say, oh, the speed is just the square root of that. Make sure we're not getting rid of, by the way, these two together. Did I ever solve what that was? Should have solved what that was for 4 sig figs, but 4 sig figs was that the, we had already have it in account 1.571 times, so this is the 3.467 squared. So we can square those. Take the 1.11111, probably lots of ones, plus square root 3.641 meters per second would be the speed. I think this is a better question because it makes you figure out that you had to do this, as opposed to just asking you directly. Asking you directly is plugging and chugging. To make you have to do this makes you the fact that you need to know to do this, right? That's sort of the nature of questions that we want to ask. For the acceleration, it's just a little bit more effort. Remember that we're going to have 4 parts to it. R double dot, R theta dot squared, ER, R theta double dot plus 2 R dot theta dot E theta. Can anybody tell me what this represents, what this guy represents? In the chat, tell me what that represents. I want you thinking. Anybody? Bueller? You guys can hit me with these little thingies right there. Tell me. Which one? I want you to do this one. This negative R theta dot squared. What is that? It's a good thought, but incorrect, Stefan. That was going to be my next question. This is the Coriolis one right here. R dot theta dot. This is Coriolis.
Is that the acceleration, the tangential acceleration? No?
You could actually say that this was the tangential acceleration, actually. If it was circular, this would be the tangential one. I could show you that. This guy right here is centrifugal. So why is it centrifugal? One thing you can tell, it's negative and it's R. So if it was in a circle, it would be pointing towards the center, right? It's also R theta dot, and the velocity, if it was a circular velocity right here, right? If it was just circular, there would be no R dot, and then so the velocity would be R theta dot. If you were to plug that back into the centrifugal acceleration, which is we usually says like this right here, right? Plug that in. R squared theta dot squared over, that's the same thing as R right there, right?
I have a question.
I just want to make sure that you recognize that there's a physical significance to each of these. This represents the distance getting further, right? The acceleration is the R dot starts to increase, right? Coming further away. This is the same thing as we have in path. The fact that you're changing directions, right? That that your velocity over at one spot is different than the other. That makes you, in order to turn the curve, you have to have centrifugal acceleration, Or centripetal, if you want to call it there. It doesn't matter. Call it either one, I don't care. This guy right here is like you mentioned, this is actually like the same thing as tangential, right? Here's the increase, here's the theta double dot times the r. That gives us an acceleration in that direction. And then this guy is the magic one, the Coriolis, the crazy acceleration. That's the combination of having r dot and theta dot. Without r dot and theta dot, it doesn't happen. So I just wanted to get you thinking and ask you a question in the midst of this. So if we plug all these things in here, that we have for the r, we take the r double dot, and that's going to be negative 1.745 minus, now we take the r 207, take the theta dot, take it and go 1.571 squared, that's ER. Do the same thing down here, take the R, which was 2.207, take the theta double dot, 3.14742, excuse me, plus 2 times the r dot, which is 1.111, times the theta dot, which is the 1.571 e theta. You do that, and you get the negative 7.19 ER plus the 3.44 E theta, meters per second squared. Now, this problem could have been asked and made more complicated, but all I asked in here was to sketch the velocity vector at the appropriate point. And basically all you need to do is draw it tangent to the path right there, right? But I think that you're going to find that this right here is going to be the 22.5 right there. Yeah, right? Because if you were to rotate that about, that would rotate there. Yeah, so that would be the same angle. Here would be the 22.5, and here's the 22.5. We could instead make this more complicated by way of, how do we know which direction the tangent is moving towards? Well, that's a good question. Probably the easiest way to do this is that, like, you could take this right here and put in for time 0. Right? At time 0, theta is going to equal 0, so it's going to be right here. So we know that we've only moved up this far. That's a good question. We could also take a look at here and say at time 0, what is radius? That's going to be 1 right here, right? So it's going to be 2.5. So we know that that's the starting point. We've confirmed it both ways. That's an excellent question because that's actually part of the thing. You want to pick it apart and think your way through it. But we could, and probably will, have some element of this that breaks it down differently. Try to figure this thing out right here. Let's say that we want to get to, you use the velocity equation. Yes. Oh, how do you find the angle? Okay, well, the angle, for one thing, it's because we knew what the angle was because we were in polar right here, right? Like here is the angle that's right here. But it's a good question. It's good that we, in this particular problem, in this particular scenario, that's how we would find it out. But let's hypothetically make this into, let's have another part of this problem. Let's make this problem harder. How would we do that? Well, what we'd want to try to do, find that. So I calculated what the speed was. That was down here. No, we don't. We don't know the radius of curvature. We know the radius from here, but this is not, but like if you took the radius of curvature, that would be like drawing a big circle that would fit like right over on top of this. So the radius might be down here somewhere. So what you would do now, you need to take a transformation of this, right? So we would take ET and EN, and then we would have like, the angles would be kind of obnoxious to see them. Oh, this is going to be tough. They're very close because of the nature of them right here. But I've kind of drawn them kind of closer here. So we go like right here. This would be ER, and here would be E theta. Right in there. So what we'd have to do is try to figure out, based on this. Yeah, in fact, actually. Go ahead. R is just the distance from the origin. It is not the radius of curvature because the path is not a circle. That's exactly right. Oh, but that's Phil. I'm sorry. I was like, wow, that was brilliant. Oh yeah, Phil. But anyway, I'm just trying to point this out right here. I think maybe I'll be making too much of a confusing type of scenario because of how close these angles are going to be with each other. So I'm not going to proceed further. But I just want to tell you that the problem could be made to ask you about this. All right. We have other requests for another problem. The thing I want to go back to, when you have a polar problem, variables of interest. And sometimes we might want to go backwards. There are problems I have put together where we were given some type of velocity and acceleration. Maybe we know maybe somebody is traveling like in this direction, and we have an observer right here. And they're standing and they're watching, and there's cars moving from here to here, and they're watching it. And we want to know what is the R dot, the R double dot, the theta dot, and the theta double dot if we see them traveling at this velocity here, and then we have like another velocity right here, and we assume that it's a constant acceleration. We assume that there's a constant acceleration between here and here. What we have to do now is like transform this and into, in this case, is going to be like the ER and E theta right in there, so that we can have like this we see there's a theta dot and a theta double dot, and also the distance that the thing is increasing away. You have to know what this distance is, and you have to know what these angles are. But what we could do is go backwards, and once you know the speed of something or the velocity of something, you could use your coordinate transformation. Yes, this video will be posted. Yes, we can look back, definitely. But I think this is a problem that I think there is an example in the book where this problem gets put in. But I just want to give you, fair warning that this one is a little bit straightforward, right? Because you were given these things, you find the variables of interest, and then you put them into this equation. Whereas you could also go the other direction, where you're given some acceleration and velocity, and you need to go backwards given what you know about the arrangement and the coordinate transformation of this, and be able to find the individual variables of interest. So still, the major thing to know about for polar coordinates, for kinematics, the VOI, the manipulation of those two equations. So we have requests for other problems, or you can either have a specific problem or a general type of, like in the, remember these are the topics. Something with coordinate transformation, absolutely. The only way to get better coordinate transformation, by the way, is to practice doing coordinate transformation. So you have to have some, so a little bit of frustration, but then overcoming the frustration. Okay, so I think I might have to invent a problem in order to do that. Or find a homework problem that has the coordinate transformation as part of the thing. Because I don't have any in my old exams. I think, let me see, do I have this other problem here? Okay, the polar, let's see, sometimes it's going to be it's nice to do the polar, to turn the polars back into, okay, yeah, let me go back to that one that I just did. Let me do the coordinate transformation there, but instead of trying to be overly complicated, I will do, what did I do with the paper? It was over here. Instead of trying to do the tangential one, I'll just do it in a rectangular coordinates. And this is actually a pretty good one to do that in. All right, so the very first thing we want to do, so now I say, let's just say find V in I and J, right? So that's going to be our part D to this. That's part D. So what we want to do, and I'll try to make this as neat as possible here. I'll maybe try to sketch these out right here. We have our R is going to be this direction right there, our ER. Our E theta is always, from a right-hand rule, going to be over to the left of it, as you're looking this way right here. So it's going to go over to that direction. So I try to use this like a T-square here, like a square. And so we have our J, and we have our I. I'll get rid of all this other stuff. Well, it doesn't hurt to do that. So here is our theta, and here's our theta. And we know that theta, we had already said that there was going to be 22.5 degrees. I hope I didn't round that down, but I think Let's see. So anyway, we set up our coordinate transformation by saying, I like to go ER, E theta, I hat, J hat. Doesn't hurt to make a nice box around these things. And ER. Okay, so you can approach these in two ways, or you could just like think them through. I'm going to take my ER and turn it into I. What I would do is I'd multiply that ER by the cosine of theta. And it's got to be positive right here. So that's a cosine of theta to turn this into an I component. ER also has a J component going upwards. In this case, it's going to go upwards in the positive J direction, and it's going to be opposite from this angle. So it's going to be the sine of theta. Here in this one, we have E theta. We notice that it's going to go in the negative I direction, right? And it's going to be opposite from the angle, so it's got to be a sine. And then lastly, it has a J part to it, but it's going to be the adjacent side, so it's the cosine of theta. Now this is a pretty easy one when they're up like that and arranged like that. Some of the harder ones, and this is just hypothetically, that you might have your I and J down like this, and maybe the ER is like that, and the E theta is like that right there. And here's your I, and here's your J. This is an aside right there, right? In that case, the
Question on that, real quick, Professor.
Yes, sir.
The direction of ER is always going to be based off of the direction that that component is going, whether it's towards the center or away from the center, and then E theta is just to the left of that? Is that how that's set up?
Well, let me say, not the direction it's going, but the direction, the location of where it's at with respect to the origin.
I see.
Right? Because remember, in polar, the origin is like we're using some fixed reference point, and so we're looking at the particle. So the ER is just going to be aligned with where the point is and the point about which we're taking the reference.
Got it. That makes sense. Thank you.
You're welcome. Now, technically speaking, the theta could be all the way like over here. Like we usually measure it this way, but we generally don't want to give like an angle that's like larger than 90 degrees when we're communicating the thing. So we might say that the angle that we would actually have in this case, let's say that we're measuring from there, that would be the theta that we're going to use, as opposed to trying to use something that's greater than 90 degrees. In this way, I would then, if I'm going to do a coordinate transformation based on this angle, got to be careful with that, you would say that the ER is going to be negative cosine of this, right? Because ER is coming here, but the I is in the negative, it's going to be have a negative I aspect and an adjacent one, so it's negative cosine. It would have a negative sine, because this is the negative J aspect right here, so this would be a negative sine of theta. This guy would have a positive sine, sorry. And it would have a negative cosine. The pattern that we always want to look for when we're making these things out is that there's going to be a diagonal nature to this. And one of them is going to have a different SIGN sign from the other ones, right? It's going to be negative while the others are positive, or it's going to be positive where the other ones are negative, like they are in this case. But there could be different scenarios. Now recognize when you have normal and tangential coordinates, you might have the curvature in the other direction. So you won't always have this right-hand rule thing going on. It could be flip-flop, but you'll still have the properties that they'll be diagonal and one of them will have a different plus or minus than the others. So going back over to this problem right here, once we have this set up and we want to get the velocity, we take the velocity that we knew, and I'll just go ahead and use, here's what the answers were up here, and we want to take the r component and multiply it by this much of I, this much of j, right? So we take the negative 1.11 multiplied by the cosine of 22.5 I plus sine of 22.5 j. Then take the E theta component, 3.47 multiplied by the negative sine of 30. Did I say 22? Yeah, 22. I said 22.5. Yeah, okay. And I, right in there, plus my 3.47, and now times cosine of 22.5 j. I had to reply to my daughter because, you know, if you have a daughter, when you guys have daughters, you'll know. Do anything for your daughter. 1.11, actually I have no, it's 1, 22.5, take the cosine of it. Whoop, I just did something. Oh, I'm still in radians. Here is something to remember. Change calc back into degrees. When done doing a calculation, like we did over here, where we had to use pi and radians and stuff like that, make sure we turn it back in, because I just got like a negative thing. I'm like, what? How can I get a negative? Well, so we go back to modes, and I go to degrees. Okay, I'm back into degrees. Yay, there was much rejoicing. 22.5. And that should be negative. And then the 3.47, 22.5 sine, and this should be negative, so I'm going to subtract right there. So we get like a negative 2.35 for I plus, let me do, I have a reason for doing this, just, you know, 22.5, take the sine of it, multiply right there. Yep. And then, well, this last one right here, 3.47, 22.5, take the cosine, multiply those two, and then that's going to be positive, so we add this together, and we get 2.781 J, and this would be meters per second. So when we take a look at that, we see, well, that's going left, and that's going up. Yes, it's going left, and it's going up, so I'm confident here. Let's take what the magnitude of this is going to be. Too lazy to write it out. Take that squared, flip them, that squared, add them, square root, 3.643. That should have been that, right? It's like a check. Yes. Some rounding errors taking place right there. And then we can also figure out what the rise over the run is. So we can take like a theta and take the inverse tan of the rise over the run, 2.781. I hope this comes out. I'm a little concerned, but we'll see. We can hope. Let's see. 2.781, 2.354, And I'm going to take the arctan, and I am concerned. Okay. So, did something wrong, I think. I was expecting it to be the complement of 22.5. Yeah. Yeah, I know. I'm taking the negative, but I'm just looking at the quadrant. Like I'm just going like up in there. So I don't know what I did wrong. I got the right magnitude. What was I expecting to get? I was expecting to get 67.5. So 2.781. All right, I'm not going to spend time on it. I'll figure it out in a bit. Yeah, Well, I'm not going to mess around with it. Yeah, and actually, I don't think it necessarily has to be that 22.5 now that I'm looking at it. Yeah, you don't necessarily know that it's going to be. Yeah, you don't, yeah, I'll take it back. I'll take this back in terms of that angle. I don't think it necessarily has to be 22.5. Because we don't necessarily know what the slope of this line is, only that's, yeah, the theta would definitely be the 22.5, but not necessarily the tangent. So I gotta take that back. Okay, sorry about that. This was not true right up here. Because we could have something that was like going like this right there, right? And here would be the angle onto the thing, but it's not necessarily going to be the angle of the slope of the thing. It's the slope of this is not dependent on the angle that's right there. That's what I'm saying. So I misstated when I put it in. So let's look at another problem. That was a coordinate transformation. We went through that with a lot of energy and vigor. You're welcome. So nobody can see me really well right here. I can just put my skull cap on. No, this one looks stupid. No, I did. My hair's getting in my face. I need to get a haircut. Got requests? I figure I'm going to go another hour, just so you know. So you don't. It'll be recorded, so you don't have to stick around if you don't want to. I mean, you know what's going to be to the most of the most benefit to you. Number 2. I like number 2. 2's good. All right. Michael Jordan. I love me some MJ. Good old projectile motion problems. It looks right to me. It's a second quadrant vector. Yep. I think I figured out why I was not getting what I expected it to be, because I was thinking in terms, I was misthinking. I shouldn't think. No, I should think, definitely should think. So let me see here. Michael Jordan shot a three-pointer 24 feet from the center of the 10-foot high basket to win the game. The ball was released 8 feet from the floor at a 30-degree angle. What was the ball speed in feet per second as he released it? Well, the number one thing that you could go to when you have a projectile motion problem is to recognize that there is an x direction thing happening and a y direction. This is a constant velocity, and this is a constant acceleration. So in the x direction, we have this. Let me put it this way. Sorry. And here we have those two things happening at the same time. So we can also sometimes, but also sometimes we might also want to use that the velocity in the y direction is going to be the original velocity in the y direction plus, minus gt, or even the velocity in the y direction squared. It's going to be equal to the velocity in the y direction squared, the original one, minus 2g change in y. But this problem fits pretty well by putting them up right here. You notice that time is not involved in this. So I think the most common way that we would approach this is to solve for time here and put it back into here. There are sometimes alternate approaches that we could that we can use, where we can actually solve for time. And I think this is actually one of those problems where we might be able to solve for time and put it back in. But let's just go through what I would think is a typical process here, where we take this equation right here and solve for time. And quite often what we want to do is like make a decision what our coordinate system is going to be. And what did I decide? Let me double check to see if I decided the same thing. Yeah, I decided that what we're going to do is make a coordinate system that looked like this right here, where this is x and this is y. All right, so I decided that the origin was going to be right over there. So solve it, that makes it nice, because then I can just get rid of that and say that I have x over VOX. I also, for convenience, say that VOX is going to be VO times the cosine of theta, calling that theta, and VOY equal VO times the sine of theta. That's useful. So when putting this into here, I'm going to say that it's going to be VO cosine of theta. So I take that and put that into this equation right up here. So I have y is equal to YO plus, and then I'm also going to substitute this at the same time right in there. So I say VO sine of theta, and, oh, not time. I'm going to substitute for time, right? And I'm going to put that VO underneath it. That helps me because I can cancel those velocities out. And then we'll go and put the 1/2 g, substitute time, remember, so it's got to be squared. So this squared, x squared over VO squared, cosine of velocity. Cosine of this. I got to make sure that's squared. Oops, almost forgot. Because I'm putting this guy in there for the time squared. So another thing I could notice is that guy right there, he turns into the tangent of theta. That could be kind of useful to us. So now what I could do is I could plug in the known things, right? So the y at the end is going to be 10 feet. The initial y is 8 feet. The angle is 30 degrees. The X position is 24 feet away. Gravity is 32.2 feet per second squared. The X is again going to be 24 feet, but it's squared. VO is what we're trying to find, and then the cosine squared of the angle that we know. So we have isolated the thing that we're trying to get. A little bit of math. We end up with 32.29 feet per second is what he has to shoot at to land it right there. We could also have solved at one point, solved for time, but I don't see where I have it right in there. Oh, I see. What I could have done is I could have left this out right here. So that's what sometimes there's a trick to do, is that I could rewrite this equation down here. I could rewrite this as y is equal to yo plus that x times the tangent of theta minus 1/2 g t squared. Now the unknown is time, right? But I know this, I know that, I know that, I know that. That's the only thing I don't know. So I could solve for the time, and I could actually plug that right back into this, and I could find my VO. See how clever that is? Oh, gravity's negative right here. I don't know if we see that. Anybody else have any questions? I don't see a question.
My question is, when I'm like doing the math out, we get like a negative number in the square root, and that's where like I'm stuck at, and that's why I'm getting confused why gravity isn't negative. I get you said it was negative. It's
Yeah, this is negative. This is negative right here.
Yeah, I am including the 10. Because when you do 10, 30 times 24, and then you subtract that to the other side. I don't know. You just did.
Yeah, so let's see when. Don't mind my crazy calculator. Yeah, we're gonna have 2 right here, right? And then we're gonna take the 24 and the tangent, right? Multiply that. Yeah, so you get like 13. But that's you're gonna bring that over. It's gonna be negative, right? So you're gonna have like a negative 11.85 or something over here on the left-hand side. But that's negative as well, so those 2 negatives will cancel out. And you should be okay. Just mess around with it a little bit, and I think you'll find the algorithm. But I'm totally with you. By the way, I mess up I mess up on those things a lot. I have to, and it's actually good practice to get that out of the way when you're preparing for the exam. Anybody else have a question? How about any requests? We haven't done a relative motion problem yet. Okay, see, I see 14. Let's check them out. See 14. Depending on how they get numbered. 14. I see 13, 14. It's a good idea. Do a dependent motion problem. Pulley problems. Everybody loves. That's not true. They don't look those books. Okay, so this is someone's calling it a constrained motion problem. I think I go dependent motion, but whatever you want to call it. Apples, oranges, nothing like that. Case or elsewhere. All right, so this thing that looks a little out of focus to me. Can we do a better job focusing? Focus, focus. Oh, good. Okay. Thought my eyes were going. All right. So we have this elevator. We have an elevator. Doesn't look like an elevator, but I guess that's an elevator. It's moving downwards with a constant velocity of 4 meters per second. We want to determine the velocity of cable C and the relative velocity of the counterweight W with respect to the elevator. What you want to do in any of these is start off with a datum. It's good. It's nice to have just one datum. You only need one datum in this problem. So what we could do is we could make this called, let's call it just S. I like S. Could have called it Y if we want to. There's W to this point. See, I'll make it go down to here. SE under that point, and then S, we call it C. So now we want to get the lengths. And we notice that there's actually 2 cables right here. So you got to be careful with those. So we go cable 1. The length of 1 is going to be this right here, which we'll call SC. And then there's 2 SEs. We take the derivative of this, VC plus 2VE. We were told the velocity of E, let's say that and let's say the down is going to be negative right here, right? So we have to say, oh, and by the way, we can write that the velocity of C is going to be negative 2 the velocity of E. We're told that the velocity is 4 downwards, so let's say it's 4 downwards. We end up finding that it's 8. So that means it's up. So this thing's going up as that one goes down. It's going down by twice as much. But you can kind of even just like, you can actually just sort of reason that out by looking at the thing on one level. And then we want the relative velocity of the counterweight. So we want to make sure that we're keeping these things straight. We could say that the cable 2, the length of the thing, is going to have, well, that's not too hard right there because it's just SW plus SE. So we know that if the elevator is going down, right, and we're trying to find W, right? So velocity of W is just going to be 4 meters per second up. So let's just say the velocity of the elevator is 4 meters per second down. So if we want the velocity of the counterweight with respect to the elevator, we write that velocity of the weight with respect to the elevator is the velocity of the weight minus the velocity of the elevator. That's the definition. You say that minus 4. We find out that it's going to be 8 meters per second. It's going to be positive 8, right? Oh, and this one should have a hat on them too, because you got a magnitude and direction, it's a vector. This on one level is like maybe a little too easy of a problem. I don't know. Notice that the original one, actually, you don't even see it there. You don't see it in mine. The original, this was a 20-point problem. So there were probably much harder problems on there. We haven't really done, well, this is sort of quasi-relative motion problem. Can we do problem 11? Yes, actually I was just looking at that. And the solution that I see that's going to be posted is actually, there's nobody in this room. I'm going to close this door and I'm taking the mask off. I'm driving nuts. Okay, cool. And I'm sweating, so I'm taking the jacket. No jacket, and the sweater. Okay, so we got a relative motion and path coordinates. So at the instant shown, car A and car B are traveling at 55 miles an hour and 40 miles an hour respectively. If B is increasing its speed at 1,200 miles per hour and A maintains constant speed, determine the magnitude and direction of the velocity of B with respect to car A. The magnitude and direction of the acceleration of B with respect to A, car B moves along the path having a radius of curvature of 0.5 miles. I think in this problem, the solution here, they just kept everything in miles per hour. I generally probably would change things into feet, but they gave everything in miles, so it's not going to hurt anything. It doesn't hurt when you're working through a problem to write down the main equation you'll eventually going to be able to need. We're going to want to find B with respect to A. So we're going to have the velocity of B with respect to A, which we know is the velocity of B minus the velocity of A. We're also going to want to find the acceleration of B with respect to A. So that's going to be the, oh, jeez. I'm getting a little tired here. The acceleration of B and the acceleration of A. All right, so I'm just checking out to see what he did. This guy's going 40 miles an hour. It's probably better that if I were to have rewritten out the solution that's eventually going to be posted onto this thing, so that we see the coordinate transformation of this piece, because this is going to be ET, and because that we didn't use the coordinate transformation at Coast Guard, so it just isn't. It isn't in Beer-Johnston, so that's not the way that they were approaching it. So here's I and J, and the center of curvature to this thing is going over to that direction right over here. So that's why this is going to be En, right there. I think I got that right, yeah. And so if we're taking a look at the angles right here, here is that theta, that's going to be the 30 degrees, and that's going to be the same angle as this right here. So what's a good idea when we're doing this relative velocity or relative acceleration is to get, they need to be in the same coordinate system in order to be able to do this comparison. So what we want to do is we're going to write out the velocity of B is going to be 40 in the ET, right? It's in the tangential direction. So we take our coordinate transformation matrix here and say we have ET and EN and I and J. And so now we're going to have, this is going to be the, for ET going across right here, we're going to have a negative cosine of theta and a positive sine. And here we're going to have a positive sine for the En and a positive cosine. So when we come to this one right here, what we're going to do is we're going to say that VB is equal to the 40 times the negative cosine of 30 I plus 40 times the sine of 30 J. What we're left with is a negative 34.64 I and a 20, turns out, J miles per hour is the units we're keeping it in. So we also know that we were also given the velocity of A, and we know that it's going to the left right there, so it's negative 55 I miles per hour. So coming back to our equation right up here, velocity of B with respect to I is going to be velocity of B, negative 34.64, minus in the I direction, plus velocity of B is 20 minus 0, so nothing in the J on that one. So what we're left with is, did I do that right? Yep. Ends up being 20.36 I plus 20 J miles per hour. And we wanted the magnitude and direction, so we get .54 miles per hour. And for an angle of the thing, we notice there's both positive, so it's going to be in the upper right quadrant, the first quadrant, and the angle is just going to be the inverse tangent of the rise over run. So it's going to be close to 45 degrees, right? You can expect it, 44.5 degrees. So I would use that quadrant symbol when writing the thing out. Or write it out as a vector. It's probably the best way to write it out, 28.5 miles per hour, 44.5 degrees. And then for the second part of the thing, because we already have the this up here, so it's not too terribly difficult to do. We have the magnitude of, let's see, I don't want to skip out here. Okay, so let's take the acceleration of, which one, B. All right, so A is going to is A changing anything? Let's see. It's a constant speed. Interesting. I'm looking at here why he is doing this. I don't know if we need to do a coordinate transformation. Oh, in order to find the direction, we need to, yeah. It will help us a lot to find to find the direction by way of doing this. Yeah. Yeah, but see, this seems like a kind of an unnecessary step, but we'll do it anyway. We know that we have the tangential and v squared over rho is the normal direction. So they're already telling us that it was increasing speed. So at 1200, and I guess it will say that these are miles per hour squared, yeah. And then here we have we know that the speed is going to be, oh no, its speed is already, yeah, 40 squared, and the thing is at 0.5 miles long. And so this is miles per hour squared, which is a weird thing we don't usually use, but that doesn't hurt us at all. So 1200 ET, and this as a value is 3200 EN. Now we can find the magnitude of this. We don't need to, we don't necessarily, is it of any benefit to do the coordinate transformation first. We could just find, and by the way, going back to the original problem right here, the acceleration of B with respect to A, they said that this was a constant right here, right? That A was traveling at a constant, maintains a constant speed. So it's actually not really even necessary to go through this whole thing. It would have been a much simpler problem because we could say that the acceleration of B with respect to A is equal to B, right? So the magnitude, which is the thing that we want, is really just going to be 1200 squared. And I don't even need to calculate the thing out. I know that I'm going to get the same answer that I would have gotten. But, and then when we go to get the angle of the thing, well, now we have a couple issues. Well, what we could do is we could find what the angle of this is going to be and then add it to the 30 degrees, right? So that's something that we could have done, right? Because we have the car traveling right up here, and we know that it's traveling here with the 30 degrees onto the thing. And we know that the normal is right here. So if we say whichever way that we're going to go with the rise and the run onto this, we have this magnitude, we're able to figure out where that angle is. Like we could find out well, it's probably easier to go find that angle right here. So we could take the normal, right? So we could take this angle right here, which maybe I'll call this right here. We could find the inverse tangent of rise over run, which is going to be the normal component over the tangential component right there. And I'm just telling you about this situation, right? That we are able to do that if we take the inverse tangent of 3200 over 1200. Take the inverse tangent. We get 69.44 as part of this. And what we do now is we add that to the 30 that we already know. So we're going to predict that it's going to be obviously 99.4 degrees, that direction, but we would prefer to go in, from a quadrant that's like this right here, right? We'd rather have that quadrant. So it's just going to be 180 minus the 99.44 degrees, which would, let's see. Yes, get us the 80.5, let's call it 6 degrees. They're part of there, and if you notice, there is the solution to the thing is this direction. But some of the intention here is that you would do the coordinate transformation, right? That we have this acceleration right up here, that we would apply that to the apply this coordinate transformation to this to get it into I and J, and then find what the magnitude and the angle would be. But you could do it in either way in this particular situation. And once again, I'm looking at the solution that will be posted. I'm posting mine on Sunday morning. I should have told the other professors that, but I'm not sure when they're posting theirs. But anyway, the really good friend of mine that this is his solution to the thing. He didn't use a coordinate transformation, but in essence, that's what he did. He just didn't go through the same procedure that you would have seen that we've been using, where we make an array. I think this is a better way, but as I mentioned, we didn't do that when I was teaching at the Coast Guard Academy. And Beard Johnston doesn't do it in a formal way, but I think they should. Do we have another request? Number 12. Oh, that's nice. All right, so I think this is just a straight out relative motion problem. Where we have a bird on an Arctic tern. What is that? I don't know. A. Indicate. What does that mean? A bird tag on an Arctic tern. A. Indicates that with respect to the wind, the bird is headed 30 degrees north of east. Right. So there's 30 degrees that's happening right there, with an airspeed of 25 kilometers per hour. At the same time, tracking devices on a scientific snowmobile, that's a scientific snowmobile, never seen one, indicate that the relative velocity of the bird with respect to the snowmobile is 23 kilometers per hour in the direction of 33 degrees north of east, like 33 degrees north of east. Knowing that the snowmobile is traveling due south at 15 kilometers per hour, determine the velocity of the bird, the wind speed, and direction. So these can be really confusing unless you try to do them systematically. So it's a good practice there to maybe just write this out. Write out what is being said in the thing, right? Indicate that with respect to the wind, the bird is going 30 degrees north of east. The bird is headed 30 degrees north of east. Okay, now they're calling this A. Okay, so this is A, and I'm looking for the 25. Where's the 25 in this? Huh, I'm sorry. I got distracted by the, in this case, indicate that with respect to the wind. Okay, I guess I need that later. Yeah. don't necessarily need that right here at the top. Yeah, it doesn't actually answer part B. This doesn't answer part B. Interesting. Okay, well, we'll have to solve that at some point. All right, so at the same time, the tracking device on this indicate that the relative velocity of the bird with respect to the snowmobile. So this is going to be the bird with respect to the snowmobile is going to be 23, and we'll just keep everything in kilometers per hour, and working there at 33 degrees. Okay. And we know that the snowmobile is going 15 kilometers per hour south. Well, all we need to do is really find what the velocity of the bird is going to be. Well, I think sometimes it's easier for me to write this thing out instead of trying to play around with them. Say the velocity of A with respect to B is equal to the velocity of A minus the velocity of B. So we want to get the velocity of A. We're asking for the velocity of the bird. So we say the velocity of A is equal to the velocity of B plus the velocity of, wait, did I write this wrong? I think I already wrote, right? Yes, okay, we're okay. Second guessing myself, that's fine. So let me write this as vectors right here. Here you go, this is going to be negative 15j, right there. And it's going to be plus, and here we're going to have 23 times the cosine of 33, I plus, and maybe I'll put it aside there, 23 times the sine of 33j. So all we're left with is, when we work this thing out, is going to be a, this right here is 19.29 I plus, and this turns out to be a negative number, negative 2.473 J kilometers per hour. So it'd be good to know what the direction of this is going to be, so we find the magnitude and direction. We get 19 point, I wish there's more sig figs here, but they didn't write it down. My good friend, Dr. Alicia Garcia, didn't write that down. And then the angle of this is just going to be the inverse tangent. And I don't bother with the signs on this. I just happen to know which quadrant it's going to be in. So instead of putting signs inside of this right here, I find that it's 7.31 degrees, so that I know the velocity of A is going to be equal to 19.4 kilometers per hour. And it's coming this way right there, right? Because it's positive x, negative y, must be that quadrant at 7.31 degrees. Now, it's not written down here. We don't have the other part of the answer, so hopefully I'll remember to fix that at some point. But one of the wind speed and direction, right? So one of the things we were told right at the beginning was that the tag on the bird, for some reason, it's a magical tag that can measure things with respect to the wind, is going to find that it has 25 kilometers per hour, and it's headed 30 degrees north of east, right? So the velocity of the bird with respect to the wind is equal to 25 kilometers per hour, and it's headed 30 degrees. So what we need to do here is now just write out and we want to find the velocity of the wind. So the velocity of A is equal to the velocity of A with respect to the wind. It's velocity of A minus the velocity of the wind. So if we want the velocity of the wind, all we have to do is take the velocity of A and subtract out the velocity of the wind with respect to A. Did I do that right? Yeah, they just flip-flop. So you take the velocity of the wind. We already have this as a vector right in here. So we take, I could write this a couple of different ways. I think I'll write it this way. I'm going to have 19.29, and I guess I'll just go right this way. Sure. Negative 2.473, and J, and then I'm going to subtract out my 25 cosine of 30. Did I read? No, yeah, it's up there. Okay. I plus 25 sine of 30J. So I'm going to take my 19.29 and my 25, 30 cosine times, subtract it out, and negative 2.361 I plus my 2.47473 473 enter, oh, they gotta make it negative, and 25 sine, yeah, 25, 30 sine times, that's gonna be minus, right? So it's a minus 14.73 J, and ran out of paper. I can keep writing. Okay. So my velocity of the wind, 2.361 squared, 14.73 squared, and both in my calculator still. No, they're not. 2.361 squared, add them together. The square root, I get it, that's going to be 15.16 kilometers per hour. The angle, inverse tangent of 14.73, 2.361 is going to be a pretty big angle. 14.73, 2.361. It's going to be like 80.89 degrees. So if I was going to write that thing out as the velocity of the wind, they're both in the negative, so it's going to be in that quadrant 3, right? So it's going to be right down there of the 80.89 degrees. Ooh. Okay. More requests? I got this ugly one right here. Just an extra problem, extra bonus problem. It was a really long one though. I even wrote on my solution to it. Much too long. So I didn't answer. I didn't do this problem. I don't know if I can. I don't know if I have the endurance to do it. 8. Okay. Let's ask for 8. There you are. More polar. And this will be the last one because my shoulder is really hurting. Oh man. Complaining about old things. I'm not that old. I'm only 51. And this is a Dr. Alicia Garcia problem. All right. Oh, I see. Okay, this is actually polar and path. The robot arm moves so that P travels in a circle. So I guess it's really path about point B, boom, which is not moving. That's fortunate. Knowing that P starts from rest and its speed increases at a constant rate of 10 millimeters per second squared, determine the magnitude of the acceleration when T is equal to 4 seconds. The time for the magnitude of the acceleration to be, 80 millimeters per second squared. Okay. So, we remember that our total acceleration is going to be the tangential acceleration, which is really the speed change, plus the velocity squared divided by the radius of curvature, and the radius is given as 8 meters. Let's keep everything in millimeters. And the way that it was expressed right here, that the speed was changing at 10 millimeters per second squared, that's the tangential, which is right here, right? That's the dv dt. So we can just write out that it's 10 et plus r. Okay, and she did it in one step right here, but we could figure out the velocity after 4 seconds. Maybe I'll write that out. It's going to be the original velocity, which is at rest, plus the acceleration, which is 10 times our time, which is 4. So we come out to be 40 millimeters per second, right? What I used was the velocity, original velocity plus the acceleration times time. So the simplest of constant acceleration equations. So what we're left with is a 40 squared over an 800. And did you ever find the answer to that? Oh, that ends up being 2. Not very exciting. And I'm like a stickler for like saying, you know what, don't drop sig figs, but she just said it was exactly 2, so it doesn't really matter in the big picture of things, but I said don't do it. And these are millimeters per second squared. So the magnitude is just going to be 10 squared plus 2 squared, which isn't really exciting. It's like 10.2. So that's part A. Part B, the time for the magnitude of the acceleration to be 80 millimeters per second squared. Well, she did it in one step, or she did it, put in the thing in there. I would do the same thing here, where I would just, now let's say the magnitude was AT squared plus AN squared, right? So I'm going to say 80 is equal to, well, we know that this is still 10. So we could find that the AN for that was going to be, I think this way makes more sense, where we take 80 and let's square it, and then we're going to subtract out 100, and then we're going to take the square root of it, and we're going to find that that's 79.37 millimeters per second squared. And then from that, we know that that's going to be v squared over rho. So v squared over 800. So v is going to be equal to, we'll multiply that by 800. Take the square root of it. We get 251.99 millimeters per second. Oh boy, she made this really confusing here. So now we need to know at what time does that happen. Well, we just go back to our velocity, original velocity plus a t right in here. And we happen to, so that's 0. We know this right here is the 10. So that's the t, is 251.99. So t is equal to 25.2 seconds. She made it more complicated, I think, by keeping the time in there. I think this looks a little bit simpler right there, and just more logical that you would go and you would solve for the velocity, and then go in and solve for the time, knowing that this was, the speed change was at a constant 10. But if you take a look at her solution right in there, she put it as like, right here, that's squared, and then that's squared, and then this right here, and she had this to the 4th, and it comes out to the same thing. Don't tell her I was criticizing her. She's a good friend. Well, that's about all I could do for today. I hope this wasn't, I recognize this in the nature of it. We're doing it remotely. I don't know how to not make this a passive experience. I don't want to do the work for you. I want you to put these together, and maybe I would suggest the best approach is to pretend you have amnesia, and to take these problems and forget that you saw the answer to them. Put them out of your mind, and try them out. Go through them and put yourself in a quiet place, simulate taking the exam, and I think by doing that you will have a much better outcome than just looking at the problems and trying to quote-unquote study them. By exercising the gray matter, and you'll be able to puzzle through. I also suggest that you pick a problem out of the book. I mean, that's why you have the textbook, and you have the answers in the back of the book for a number of problems. Not the solutions, but the answers. I got to tell you, this is how I succeeded really well in college. Was I didn't have a whole lot of the of worked out problems. What we had was these right here, right? We have this. You go into the back of the book, chapter 13. Here's the answers to select problems, right? In fact, there's almost all of them. I guess they leave out a couple of them every now and then, but practically all of the answers there. And the thing about doing it this way, it's like, it is frustrating. It is frustrating. There's no doubt about it. But it is satisfying to get the right answer, and it really pushes your brain. It really will be frustrating, and you don't, and of course, what you could also do is you could probably find the solution manual somewhere, somehow. Don't, but you could. But if you push your brain in this way, man, you're going to be surprised at how easy an exam feels when you have prepared by taking a problem and just gutting out. Just keep pushing through until you figure out, where did I go wrong? And I'd also I'd really make a push for you to practice solving the problems for speed as well, because I find many people are very slow and methodical, which is a great benefit as an engineer. It's a terrible trait to have as a test taker. So I want to see people succeed. So I try to give them advice. Hopefully they'll pick up on that. All right, Phil, thank you. Everybody have a great weekend. I know, it'll be a great weekend not studying, practicing problems for dynamics. No reason to study, practice problems. Thank you, guys. That is all.